Okay, in this video I will show how you can write a test bench and simulate any Verilog module or any Verilog design using that test bench using the Quartus design environment and Modelsim. So the first thing I need to do is go to File, New, Verilog HDL file, and I'll just paste my Verilog module code into this .v file. So the code I've written here is one of the simplest modules you can write in Verilog. This is just a very simple 4-bit counter. And let's say we want to test the functionality of this module. So, one of the things we would want to do is just check that this is behaving as a counter and just check that the value of count is incrementing on the positive edge of clock. So there's a couple of things we need to do. And what I would say is if you are a beginner, make sure you watch carefully because there are a few steps in this process that are not so obvious. And many people new to this workflow, they slip up, even with something easy like a simulation using a test bench. So make sure you watch carefully. So I have my counter module. What I need to do now is just save this counter module in my project folder. So I'm going to give it a name, and I like to give the .v file name the same name as the module name. So that's called counter. And one thing you should always look out for is whether that .v file appears in the project navigator under files. Okay, by default it shows hierarchy, but if you go to files, you'll see all of the .v files in your project at that time. And that's important because when you want to instantiate modules in Testbenches or other Verilog modules, your module has to be in the project navigator here to make it available to that project. Okay, so what's the next thing I need to do? Well, if I want to test this module, I need to write a test bench. And the purpose of a test bench is, well, it behaves in many ways like any other Verilog module. By definition, it's the top level entity, so you can't instantiate a test bench within another Verilog module. It is by definition the top level. But its only purpose in life really is to test and instantiate other Verilog modules within it and to produce stimuli signals to test the functionality of the modules within it. So in our test bench, we would want to make a clock and we would want to monitor the value of count. So let's go ahead and make a test bench. So to do this, we need to go to File, New, Verilog HDL file. So it's the same process as making any other Verilog module. And I'm just going to paste in some code I wrote earlier. Now this is a test bench. Okay, so now it does look like any other Verilog module here, but there's a few key differences. First difference is this first line. So this first line is the timescale and precision command. Now this is really important for a test bench in Verilog because the timescale determines what this means. We'll come to this later. Okay, you've got a hash command here. Now that is absolutely fundamental to the way test benches work and the way that we generate signals. Okay, and that all depends on the value of this timescale. We also have a precision. Now, in this case, I've got a precision of 100 picoseconds. Now, you can think of that kind of like the sampling rate of the test bench. If you're a beginner, don't worry too much about the precision. You just have to make sure that it is less than or equal to the timescale. It's usually better just to make it a bit lower than the timescale. Now, the module name, I like to give them descriptive names. You can call the test bench anything that you want, but I always like to give it a descriptive name. So I've called it test bench. Now, notice the difference here between the way that we define the module here with the signals within the brackets here, clock and count, they're the signals coming in and out of the counter module. Now, as I said before, the test bench is the top level entity by definition, so it doesn't have any signals coming into it or any signals coming out of it. So we have to make sure that there is nothing within those brackets, or as a shorthand, we can just leave the brackets out. Now, I mentioned the importance of the timescale. What the timescale means is, well, it defines how long one time tick is in the simulation. Now, notice here I have an always block, okay, and I've basically made a register called clock. I've initialized that register to 0, and then I have an always block here. So an always block means it will just carry on forever, okay, so it will, well, what this will do is delay by 10. So delay by 10 means delay by 10 time ticks, which means, in this case, delay by 100 nanoseconds. Okay, if it was delay by 1, it would mean delay by 10 nanoseconds. But you can configure this to get whatever clock frequency you need. Okay, so this will mean delay by 10, and then clock is equal to not clock. And can you see how that would make the shape of a clock? Because it would go, I'm not going to try to type it out, but it would make the shape of a clock, because it would spend 10 time ticks as 1, then it would spend 10 time ticks as 0, then it would go back up to 1, and so on. So that's making a clock for us. So that's a very convenient way to generate a signal. Now, this would also work if you needed to make any other arbitrary type signal in a test bench. This same principle would also work. Now we get to the issue of, what is this test bench actually doing? Well, at the moment, it's just generating a clock. What we want this to do is to actually instantiate a module for us to test, okay? And the one we want to test is this counter module. So what we have to do is actually instantiate the counter module somewhere within the test bench, okay? And there's a couple of ways you can do this. But the way that I do it, and this is kind of like a shortcut, is I right-click the .v file and I select Create Verilog Instantiation Template File for Current File. Okay, now I will save the test bench as test bench, and now it will make an instantiation template file for the counter.v, but we've got some errors. So let's just see what these errors are first. So procedural assignment at 10. So if I double click the error, what this is saying is procedural error counter object count on left-hand side of assignment must be a variable. So of course, I forgot to make that a reg. So let's just try again. That's a good thing about doing this, is it does do a basic check of the code, and that is successful. Now, the advantage of doing this is we can now go to File, Open, and you can see we have this new .v file called counter.inst. If I double click and open this, it gives us a convenient template that we can copy and paste into our test bench. So it's just a way to save time. Okay, so if I paste that in, this gives us the correct way to instantiate a module within a test bench. And it's also the same if you want to instantiate a module within any other Verilog module, because you can instantiate modules within modules in Verilog. Okay, and you can see the way it's done. This is the module name, so it matches the name of the module. And then this is the instantiation name. So, what we could do in a test bench is actually have more than one instantiation of counter, but we would have to make sure that the instantiation name was different, like this. For now, let's just stick with the one counter. Now, we do have to be a bit careful here, because the automatically generated signal name here, clock sig, that's different to the name within our test bench. So what I'm going to do is, just to make life easier, I'm going to change all of the clocks within the test bench to match the clock name that was automatically generated by the template. And what this means actually is .clock. This is the port of the module, so this is matching what's here. And in brackets, that's the signal name within our test bench that we want to apply to that port of the module. Okay, so clock sig is an input, and then count underscore sig is an output. Okay, now notice here that this clock underscore sig is a register because we make that within our test bench. But the question now is, how do we define the count signal within our test bench? Well, this is being continuously driven by the counter module. So we define this as a wire within our test bench. So I'm going to define this as wire. We know it's a 4-bit wire, and the name is count underscore sig. And basically this wire just picks off the output of that counter module. Okay, I think we're ready now. So if we just save again, next step, this is important, make sure you set the test bench as the top level entity, like so. And then we will do the next crucial step. This is one of the steps that beginners forget to do or don't know that they need to do it. We need to go to assignments, settings, and then we go to EDA tool settings, simulation, and we have to make sure we set our tool name. So the simulation tool that we'll be using is Modelsim Altera. That should come with the Intel Prime Design environment. And then we have to tell Quartus that we have a test bench that we want to simulate. Okay, so in the native link settings, we go to compile test bench, test benches, and we just have to register the test bench within Quartus. So we type the test bench name in here, and then we go to file name, and we have to select the .v. And make sure it's there, hit OK, hit apply, hit OK. And now, once the test bench is registered within Quartus and the native link settings are set up, we can go to processing, start, analysis, and elaboration. So analysis and elaboration is the only process that you need to do if you do RTL simulation. Okay, now we've got an error, so let's see what the error is. I like to double click the error, and the error is saying HDL syntax error near text 10. And I just wondered if I've used the wrong symbol there. Test, oh, instead of, okay, that's a deliberate error. That should be timescale, not test bench. Okay, save, and we'll do that again. So that should be timescale. Deliberate error, just to make sure you're staying awake. Oh, another error. So let's go double click, and what's this error? So clock must be connected to a structural net. So clock, let's see. Okay, another deliberate error. If I go to counter, that should be input clock, not in out clock. I shouldn't do videos this early in the morning. Now let's try again. Start, processing, start, analysis, and elaboration. Hit yes. Wait a few seconds for the analysis and elaboration to complete. This time it's complete. So a couple of deliberate errors. You always make errors in however simple the project is. I always make errors, but the key thing is that you are able to resolve the errors quickly. So once that is done, we can go to Tools, Run Simulation Tool, and then RTL Simulation. And this should open Modelsim. Now, if this doesn't open Modelsim, you might need to go to Tools, Options, and you might need to make sure under EDA tool options that the path to Modelsim is correct. And this is the path that you need to point to for Modelsim Altera. So the equivalent of this on your system, and it's this one here. That's the key folder to point to. Okay, so Modelsim has opened. This is the wave window. So we've started simulating. So what I'm going to do is I'm going to go to simulate and break. Simulate, break, just to stop the simulation. Now, the reason I needed to do this is because in our test bench, this clock is in an always block. So that will just continue forever. So if we just went away and made a cup of tea, came back, it would still be simulating the same thing again and again. So you only need a couple of cycles here to know what's going on for something as simple as this. So just to avoid it eating into the RAM of your computer, just be ready to do simulate and break. Now, if I hit F, you'll see that's how much it's simulated. So we need to zoom in on the key area here. So what I do is I normally go to the very beginning just to see what's happening there. And I select zoom in on cursor, which is this one. Or you can hit the shortcut C. And if I zoom in, we should start to see some detail. Good, so we can see the clock. Yeah, that looks like a clock, and we can also see the count signal. Now, if you don't like seeing this in binary, you can always right-click the count. You can go to radix, and you can select any radix that you want here. So I'm going to select unsigned decimal, and then you can see in decimal the counter increasing. You can also plot the signal. So if I right click and I go to format, analog automatic, it will plot the signal. Now I've let this go for quite a while, so it might take a while for this to plot the full signal. But if I just zoom out here, you can actually see the counter increment and then roll back to 0, go back up, roll back to 0, and so on. So this is how you do a simple test bench. I'm going to close Modelsim. Now, I mentioned that we can have more than one module at the same time in the test bench. So I'm going to show you how to do this. So I'm just going to have the counter module again. So now we've got two counter modules, but we have to make sure now that we have a separate count signal. Okay, that and that are two different signals now. They can't be the same name. So I'm going to call that one count sig 2. I'm just going to copy and paste this. Okay, and now we've got two instantiations of the counter module at the same time running in parallel. So if we want to see this in action, we just save, do analysis and elaboration again, make sure Modelsim is closed because you can't have two instances of Modelsim open at the same time. Once analysis and elaboration is complete, run simulation tool, RTL simulation. And this will open up Modelsim again, and hopefully now we should see both counter signals together in parallel. So simulate, break, go to the wave window, shortcut F to see the full signal, zoom in on cursor by hitting C, and you can see we've got two count signals. So we have two counter modules running in parallel, and with your test bench there's no limit really to the number of modules you can have, and you can actually stitch together your design very easily in Verilog code just by instantiating more modules. And the output of one module could become the input of another module, and you can make very complex and elaborate designs within a test bench. But hopefully this has showed you how easy it is to make a test bench within Quartus. If I was to summarize here, the key steps, which might not be so obvious, are first of all, you have to go to assignments, you have to go to settings, and you have to make sure your test bench is registered. You only have to do that once. If you make further changes to your test bench, You don't have to go back in and do this, but you have to make sure that your testbench module is registered within the native link settings. You have to make sure the testbench is the top level entity. You have to make sure you run analysis and elaboration, and then you just have to open Modelsim using RTL simulation. Now, what would happen if I wanted to enhance the design that we've just had? So remember, we had two counter modules and they were both the same. They were in parallel, but they were both basically doing the same thing. But what happens now if I want a second module here, which takes on the output of the counter module? And what I'll say is, let's say I want a module which looks at the value of count, and if that value is less than 8, output a 0, and if it's more than 8, output a 1. So I've got a module which does just that here. Okay, so it's a new module. I've called it what if. We have an input clock. We have a 4-bit input count. Remember, that's being taken from the counter module output. And we have an output register called outstate. That's going to change state depending on the value of count. Now, to do this, I have an always block here, so always at positive edge of clock. If count is less than 8, let's say, let's make outstate become 1. Otherwise, outstate will be 0. Now, we have to be mindful here that there will be a 1 clock cycle delay here because we've basically got a non-blocking assignment here. So the update will happen on the next positive edge. So we have to expect, when we run the simulation, we have to expect that outstate will become 1 when the count is 9. Okay, so I'm happy with the code here. So I'm going to use the shortcut. I'm going to right click what if, and I'm going to create a Verilog instantiation template for my test bench. And in fact, I've already done that. And this is just a shortcut, by the way. This just saves time, so we don't have to instantiate the module manually. So I'm going to paste that in our test bench, and we can see now that the output of the counter module is now the input to this what if module. And then we have outstate. I've already made a wire here, so that will pick off the output of this what if module. So now we've got two modules which are basically interacting with each other. So what I need to do next is go to processing, start, analysis and elaboration, allow Quartus to do its thing. I'm just going to close a previous instance of Modelsim here. Once that's done, we can go to Tools, Run Simulation Tool, RTL Simulation, and we can check to see if this is doing what it should be doing. So Modelsim will take a few seconds to process, and then the wave window will pop up. Remember, once the simulation is running, you can tell by looking down here, once it's running, we go to Simulate and Break. And the wave window, if we select F to see the full waveform, of course there's not much detail here, but we can zoom in on cursor. Now count underscore sig2, that's a legacy of the previous design. We forgot to take that out, so of course that's going to be in a high impedance state. But what we're looking for here is the value of count underscore sig. We change the radix to unsigned decimal. We can see that the value of outstate is now changing when the count is greater than 8. And then, of course, when we get back to 1, or when we get to 0, in fact, the next rising edge, the value of outstate will become 1, because at that point it goes from 15 back to 0 and it becomes less than 8 again. So this is working as it should. So thank you for watching this video, and I'll see you in the next one.